In this example, we're going to talk about inductance, flux, and Ampere's law. We are doing problem 5.37 out of the book. The answer to this one is in Appendix B, but the process for getting to that solution is not there, so we'll walk you through it. The problem is, find the self-inductance per unit length, so that would be the transmission line parameter L prime for a parallel wire transmission line. So what that looks like is, if we have a cross-sectional view of this transmission line, we've got two wires. The wire radius is A, and the center-to-center distance that is separating these two wires is D. These wires are embedded in a medium with permeability mu. So on a transmission line, there's equal current carried by each conductor. So if wire 1 has current I going this way, that means that wire 2 has the same current I going the other way. We know from past problems that the magnetic field due to an infinitely long wire is, B is, if the wire's along the z-axis, it's phi hat mu I over 2 pi r in cylindrical coordinates. But let's solve that anyway using Ampere's law, because this is an example, and then after that we can do the flux integral to figure out what the inductance is per unit length for this structure. So to do that, we're going to consider just one wire. And let's say that the wire is coming out of your screen right now, so the current I is coming out of the screen like that. And we're going to align that current with the z-axis. So our current I as a vector is z hat times I, the scalar, the magnitude of the current. To figure this out, we're going to use Ampere's law. And just as a reminder, Ampere's law is mu times the integral of the amount of current going through the surface. So that's the current flux through the surface. We don't usually call it current flux, we just call it current flowing through the surface, but there you go. Is equal to the integral of the magnetic flux density around the boundary of the surface. Whoops, that's supposed to be a dl. So, by symmetry, we have an infinitely long wire, and we're going to have only a phi component for this magnetic flux density. So B has only a phi component. You can figure this out by trying to get it to have an R component or a Z component, and then finding that it would be canceled out by an oppositely located segment of current elsewhere on the wire. So for instance, if we say that, well, at this observation point, if we have a little current section over here, we can get a Z-directed component for that magnetic field, then we end up choosing another equally oppositely located segment over here that would cancel it out. And you can always do that with an infinitely long wire. So we only have a phi component because that's the only one that doesn't cancel. For similar reasons, by symmetry, we only have an R component. We only have R dependence. And the reason for that is the geometry doesn't vary with any of our other variables. The geometry doesn't vary with angle phi, and it doesn't vary along the z-axis. The only thing that changes along our geometry, the only dimension along which it changes is the radial one. So the magnetic field can only depend on R, because everything else is symmetric. You could move the origin around and get the same physical problem. So based on these two facts that we have deduced from symmetry, we can choose an Amperian contour. Here's our wire again. And we're going to choose that contour to be a circle around the wire. And we'll choose the direction of the contour so that ds is in the same direction as the current. So that means if the current is still coming out of the board, then dl is along the phi direction like that. So this integral works out to be really simple because the current flowing through the surface was given to us at the beginning. It's just I, so the left-hand side of Ampere's law works out to mu I. And that is equal to this contour integral of B dot dl, around the boundary of our Amperian contour. And since we've said that B only depends on r, but r is constant around the contour because this is r right there, and it only has a phi component, what we end up with is integral from 0 to 2 pi of magnitude of B phi hat dot phi hat r d phi. You can see this dot product works out to 1. There's nothing that depends on r, so that factor of r ends up just moving out to the front of the integral. There's actually nothing that depends on phi either, so when we evaluate this integral, we just get a factor of 2 pi. So the right-hand side of our Ampere's law just works out to be magnitude of B times 2 pi r, which means we can solve for the magnitude of B and find out that our magnetic flux density is equal to phi hat mu I over 2 pi r. So that's step 1 in this problem, is figure out what the magnetic field actually is. Now, if you remember, the definition of inductance for a structure is the magnetic flux, or really the magnetic flux linkage, but we don't have multiple turns, so those two numbers are the same, divided by the current. So let's find the magnetic flux through this structure. To do that, a lot of people think that they need to use the Amperian contour again, and it doesn't work that way, because we need to choose a contour now whose boundary is the current, right? So what we're looking at is the loop enclosed by the current, and we got to find the flux through that. So we've got current I flowing this way. This is a side view of our transmission line now. And again, we have current I flowing the other way. So our flux contour is going to have to look, I'll draw it in another color, like this. I'm not including the wires because the magnetic field along the wires is 0 anyway, but you could select this along the axis of the wires, and that would be fine too. It doesn't really matter. So we could draw it like this also, and that's also fine. The direction of our contour is going to be determined by the current, so it's going to go like that. And it has length delta L. So how do we set this up? We need to find the total magnetic flux through this surface. And if we were to draw its surface normal vector, that would be going into the board, and it would be phi hat directed, but that'll be ds like that. So how do we do this? Luckily, we have another symmetry thing that we can apply, because wire 1 contributes flux number 1 to this problem, and wire 2 has its own magnetic field from the current on wire 2, and that's going to contribute flux number 2 to this problem. But since they both carry the same current and they have the same dimensions and superposition exists, we can say that flux number 1 is equal to flux 2. And the total flux is just the sum of those two. So then all we have to do is think about the problem as though there's one wire, find the flux through this surface of the magnetic field due to just that one wire, and then double it. So the boundaries of this are, this dimension is delta L, and between the wires we start at radius A and we end at radius D minus A, because we want to stop just at the edge of wire 2. The way that we set up this integral then is that the total flux is equal to 2 times flux due to wire 1, which is 2 times the integral from r equals a to d minus a, and z equals 0 to delta L. You can choose whatever start point you want, but 0 is always a nice easy one, of b dot ds. We substitute in our value that we had for b earlier. So that's equal to 2 integral r equals a to d minus a, integral z equals 0 to delta L, mu I over 2 pi r phi hat dot, oh, and I didn't tell you what ds is. We already told you it's in the phi hat direction, but along this dimension we're varying along r, and along this dimension we're varying along z, so it's phi hat dr dz. So that'll be right here, phi hat dr dz. We can move everything out to the front of the integral that doesn't depend on r or z, so let's do that to begin with. This 2 and this 2 cancel out, so we end up with mu I over pi. And let's also evaluate the z integral because nothing depends on z inside here. And we're also evaluating this dot product, which is equal to 1. So when we evaluate this z integral, we get a factor of delta L because we're evaluating something that is constant with respect to z along z equals 0 to delta L. So we got delta L up there. And then what's left on the inside of the integral is the integral from a to d minus a of 1 over r dr. And the antiderivative of 1 over r is ln of r. So this works out to mu I delta L over pi ln of d minus a minus ln of a. And we can simplify that to be mu I delta L over pi times ln of d minus a over a because of the properties of logarithms. And that is equal to the total flux through that surface that we defined. So we're looking for the per unit length inductance, though. And in order to find that, we're going to have to divide by delta L here. So our final value for L prime is going to be that total flux divided by the current and delta L. So in the end, what we get is mu over pi ln of d minus a over a.